Hello students. So today we are going to discuss about Fajans rule. Now Fajans rule is a very important rule to decide the covalent character of an ionic bond. Understand, the Fajans rule states that no bond is completely covalent or no bond is completely ionic. So that means you would have some amount of ionic character in a covalent bond and you would have some amount of covalent character in an ionic bond. Okay, now let me explain you this first with a few understanding parts and then we'll actually move into understanding the Fajans rule. So over here, understand, let's suppose I have a bond, let's say a covalent bond of a molecule HCl. Now, we all know that in HCl, hydrogen is a electropositive element and chlorine is an electronegative element. So definitely chlorine would be partial negative and hydrogen has to be partial positive. So therefore what we say is, we say this bond is definitely a covalent bond because it is formed by sharing of electron. But then in this bond, because we are having partial positive and partial negative, that is two opposite poles, I would call this bond as a polar covalent bond. So over here, see, we can understand that yes, this covalent bond has certain ionic character. Okay, and this is what we are going to talk in Fajans rule. Now understand, Fajans rule is related more towards the ionic character of a covalent bond. Okay, so let's now understand, Fajans rule is more related towards a covalent character of an ionic bond. So right now here we discussed about what? We discussed about ionic character for a covalent bond. Okay, so the bond was actually covalent and in that we had some ionic character, right? So we discussed that over here, okay, which was very simple. It's just simply based on electronegativities and electropositivities. Okay, now if we talk about Fajans rule is more into discussing about the covalent character for which bond? For the ionic bond. So what does Fajans rule say? Now, before we understand what exactly the Fajans rule states, we need to understand that Fajans rule is more of a qualitative rule. Now, what do you understand by the qualitative rule part? This means that Fajans rule will definitely tell you where you have more covalent character and less covalent character. But he won't be able to quantify how much more and how much less. Okay, understand, you won't be able to associate a value towards it, but yes, definitely you would be able to tell who has more and who has less of a covalent character. Okay, now moving further, we are talking about covalent character in which bond? Into an ionic bond. Now if we are talking about ionic bond, that means we definitely have two types of ions. One is a cation, which is a positively charged ion, and another is the anion, which is a negatively charged ion. Now understand, before we move with the cation and anion wala story, let's understand, if we are talking about a cation is formed by donation of electron. Let me take an example for you. So let's suppose you have sodium over here. Okay, sodium is 2,8,1 with the electronic configuration. He will lose one electron and get converted into sodium positive. But understand, the moment sodium loses an electron, okay, what is happening is, now sodium has number of protons that is equal to 11, but the number of electrons is equal to 10, and therefore we can say that the number of proton is definitely more than the number of electrons, because of which the nucleus, the protons, become more powerful. And obviously the nucleus is becoming more powerful. What you would see is, you would observe that the effective nuclear charge, which we refer it as Z effective, the effective nuclear charge would be very strong. Now, if the effective nuclear charge is increasing, definitely what would happen to the size of cation? the size of cation will be decreased. Absolutely right. Okay, moving on towards the anion. Again, if you take an example of chlorine over here, chlorine is 17, so 2 comma 8 comma 7. If he gains one electron, he becomes chlorine negative. Chlorine negative will be having number of protons which are still 17, but number of electrons would become equal to 18. And therefore what has happened is the number of protons is less than the number of electrons. Due to this, the Z effective has decreased, and because it has decreased, the strength of the nucleus has also reduced. Now understand, if my nucleus is already less in strength, okay, won't it be easy to remove the outermost electrons? Understand, let's suppose if I have an atom over here, and in this the nucleus is not that powerful, the nucleus is not that strong, so won't it be easy for me to remove the outermost electron? Definitely yes. And this exactly is what happens in Fajans rule. So when we talk about Fajans rule, we need to understand about two different ions. The first one is the cation, and the second one is the anion. What happens is we need to understand that a cation is a person who is going to distort the anion. A cation is a person who has a stronger nucleus. So because it has a stronger nucleus, he has more strength. And because he has more strength, he is a person who is going to disturb the electron cloud of an anion. And therefore, for cation, we'll always discuss about something called as polarization. Okay, but when it comes in terms of anions, we would discuss anions with a factor called as polarizability. That means the ability to get polarized. So for cation, what we are going to see is we are going to talk about, in case of cation, we are going to talk about we are going to focus more on, focus is the most correct word over here. So in case of cation, we are going to focus more on how well it is able to distort, how well it is able to distort the electron cloud. Okay, and when it comes in case of anions, we need to focus more on how well the cloud is getting distorted. Now understand, I know it's a bit fast, but then understand, let's try to check over here. Okay, so I have a diagram here for your reference. Let's try to understand through this diagram. Okay, so in this diagram, are we able to see a cation which is smaller in size? Yes, so you have a cation, okay, which is smaller in size. Let me draw it over here for you. So I have a cation which is smaller in size, okay, and I have an anion which is larger in size. Definitely anions has to be larger in size. Okay, now what happens is, so when this positively charged cation and the negatively charged anion, when they come in contact with each other, or when they come close to each other, what happens is this cation, it starts to attract the outermost electron. These outermost electrons of the anion, the cation starts attracting, because of which what happens is the cation, which was normally a spherical structure, it remains spherical, but the anion becomes a bit distorted. It becomes oblong. It becomes like an egg shaped structure. So over here we can see, let me mark it for you. So over here what we can see is that I have a cation, I have an anion which are currently away from each other, so there is no distortion. But as they come closer to each other, the outermost electrons, remember I am always talking about the outermost electrons. These outermost electrons, they get slightly pulled towards the cation. Why? Because cation has a stronger nucleus. So cation is like, okay, I would try to attract my electrons as well as I would try to attract the electron of the incoming ion. Okay, so he would attract electron, and it appears, please remember, it appears as if the electrons are shared. And sharing of electron is a covalent character. So therefore what we say over here is, we say that if you're talking about a cation, let me just erase this for you. So what we say over here is that if you're talking about a cation, for a cation, you would talk about polarization. Okay, and understand, more the polarization, so if polarization increases, more will be the sharing, or more the electrons will appear to be shared. So more the polarization, more will be the sharing, and more is the covalent character. So please understand, over here what I can say is the covalent character will increase. Similarly, if we are talking for an anion, then in case of anions, we will talk about, or we will focus about something called as polarizability. Okay, so for anion, if the polarizability increases, that means it is more easy to get polarized. Definitely more would be the sharing, and more the sharing, or more the appearance of sharing, definitely the covalent character will increase. Okay, so in all majorly, these are the two characters on these are the two factors sorry these are the two factors on which the covalent character actually depends. Okay, let's now try to understand them in a bit more detail. Let's understand. So here we have something called as factors affecting covalent character. The first one, we are going to talk about charges. Okay, now understand, in case of charges, I have two types of ions. One is cation, another one is anion. So quite obvious that if I have a cation with, let's say, a +1 charge, a cation with +2 charge, and a cation with +3 charge. Okay, so who would attract electrons more easily, or who would attract electrons more strongly? It's definitely +3. So what I can say over here is +3. Let me write it as like this: +1, +2, and +3. Okay, what we can say over here is +3 would be more attracting, +2 would be less, and +1 would be the least. Okay, so where would you find more sharing of electrons, or where would you find more polarization? Obviously in +3. So what I can say for cation, that if the charge increases, the covalent character also increases. So are they directly proportional? The answer is yes, they are directly proportional. But please remember, for cations. Okay, now let's talk about anions. So in anions, let's say I have -1, I have -2, and I have -3. Now understand, more the negative charge, weaker is the nucleus. Okay, this is the thing we need to understand, that if more is the negative charge, that means more electrons are accepted, so the power of nucleus is becoming less. So therefore what I can say is, in case of anionic charges, who would be having maximum strength of the nucleus? That is obviously -1 would be greater than -2, and would be greater than -3. Okay, but now in case of anion, we talk about something called as polarizability. So what I can say is that polarizability is maximum when Z effective is minimum, and Z effective is minimum in which case? In the case of -3. So what I can say over here is, as the negative charge increases, the polarizability increases, and definitely the covalent character will also increase. Okay, understand this. Okay, so what we are saying, that if the negative charge is increasing, if the negative charge is becoming more in magnitude, I'm just talking about magnitude. I know that -1 is greater than -2. Okay, but then if it is -1, -2, -3, so larger the magnitude, larger is the covalent character. Clear with this? Okay, and why is this so? Because -3 would have more polarizability as compared to -1 or -2. Okay, now let's move towards the next important factor, that is the size of anions. Okay, now if we talk about size of anions, obviously we need to talk about size of cations also. Okay, so let's talk about first size of anion. Now understand, my dear students, if you have two anions, let's say the first anion is A and the second anion is B, both are having negative charges. Okay, but then are both of them having the same sizes? The answer is no, they are not having same sizes. So therefore, where would it be easy to remove, or where it would be easy to attract the outermost electrons? It would definitely be easy in option B, or in the case of anion B. So therefore, what I would say over here is that if the size increases, please remember we are talking about size of anion. If the size of anion increases, the polarizability increases, and therefore the covalent character will also increase. So covalent character will also increase. Please remember this over here. So what I can say for the case of anion, that as the size increases, the covalent character goes on increasing. Again, I'm repeating, this is the case for anions. Let's now talk about cations. So again, in case of cation, let me just change the color for you. So in case of cations, if I talk about, let's say I have a cation with a positive charge A and another cation B with again a single positive charge. Okay, so I have two cations. Now the problem over here is, see, understand, cation, we need to focus about something called as polarization. So smaller the cation, it would be able to go more closer to the anion, right? If the cation is very small and the anion is big, so the cation could go and easily polarize the anion, or the cation, I would say the cation would go much more closer to the anion. So what over here I can see, or I can observe, is that the size of anion, sorry, my bad, the size of cation, when it decreases, the polarization increases, and therefore if polarization increases, I would say that the covalent character would also increase. So what I would say over here is, let me write it over here for you. So the covalent character is directly proportional. We are simply talking about the sizes, not with respect to anything else. Okay, or let me do one thing, let me write it fresh. Okay, so we are specifically talking about what? We are specifically talking about the sizes. So if we talk about the size of anion and size of cation, in relationship with the covalent character, so what I can say over here is that if the size of anion increases, the covalent character increases. Why? Because the size of anion increases, it would be more easy to remove the electrons, or more easy to attract the electrons from the anion. But then if the size of cation decreases, the covalent character increases. Why is it so? Because if the size of cation decreases, the cation would be more accessible towards the anion, or the cation would be easily attracting the electrons. So therefore, I would say that the sizes of anion and sizes of cations are in proportion with covalent character. But please remember, it is the size of anion which is directly proportional and the size of cation which is inversely proportional. Please remember this, very, very, very important. Okay, let's move to the last and the final factor which affects Fajans rule, or which affects covalent character. Okay, and this is pseudo noble gas configuration. Now, understand, we don't have this in much. Okay, you won't even tackle this much, but then definitely not IGCSE, CIA would definitely ask you a few questions based on this, or at least they can ask you where you need to answer. Okay, where you need to put forward your point, not necessarily in the exact same dimensions or exact same wordings, but then at least to the crux of it. Okay, understand. So if I talk about pseudo noble gas configuration, we need to understand that all the ions, okay, which have a configuration of ns2, np6 and nd10. Okay, so all the cations, I am specifically talking about cations, all the cations who have a pseudo noble gas configuration. Pseudo means what? False. And noble gas configuration, so it is acting like a noble gas. So all the cations, again I'm repeating, we are only talking about cations over here, not about anions. So all the cations which have a pseudo noble gas configuration of ns2, np6, nd10, okay, all of these would show a slightly higher covalent character. Okay, let me give you an example. Let's suppose if we talk about copper. Copper is 29, and we know the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And yes, I know, before you say that sir has gone wrong and all that stuff, yes, I definitely know that over here from S 1 electron would go, and therefore you would have 3d1. Okay, so over here you would have 4s1. And why is it 4s1? Because one electron has jumped into the d orbital. It was actually supposed to be 3d9, 4s2, but then one electron jumps to achieve more stability. Okay, now if I consider, let's say, two ions Cu plus 1 and another ion Cu2 plus. Okay, so first where copper is in plus 1 oxidation state, and second where copper is in plus 2 oxidation state. Let me give you the compounds also. Okay, let's say the first compound I am saying CuCl, and the other compound I am saying is CuCl2. Okay, now over here what happens? Let's understand. Okay, if I talk about Cu, what would be its electronic configuration? The electronic configuration, only the outermost electronic configuration. The outermost electronic configuration would be 3s2, 3p6 and 3d10, right, for Cu in plus 1 oxidation state. Whereas if you consider Cu in plus 2 oxidation state, the outermost configuration would be 3s2, 3p6, 3d9. Okay, now if you just notice over here, 3s2, 3p6, 3d9, this is not a noble gas configuration. So over here I would say that this is not a pseudo noble gas configuration. And because it is not a pseudo noble gas configuration, I would say that the covalent character is less. Okay, and because you have CuCl, wherein Cu is giving you a +1 oxidation state, and because it is having a +1 oxidation state, it is able to show pseudo noble gas configuration. I would say that over here the covalent character is more. Okay, now CIA would ask you a question something like this, that CuCl has lower melting point as compared to CuCl2. Give reason. Okay, so what is the reason for this? The reason for this would be that in CuCl, because Cu is in its +1 oxidation state and it is showing a pseudo noble gas configuration, okay, the covalent character is slightly more. So the covalent character is more, definitely the ionic character would be less, and because the ionic character is less, the forces of attraction is less, due to which the melting and boiling point will reduce. Okay, you could also expect similar questions on certain anions, like I'll just give you the list of not anions, sorry, cations. Certain cations like Cu+1 and Cu2+ that we just discussed. Okay, you could also expect for Ag plus, you could also expect for Au plus. Okay, you could also expect for Zn2 plus. Okay, you could also expect for cadmium. Okay, cadmium 2 plus and Hg2 plus. Okay, all of these would be having a very high covalent character. Why? Because they have a very high polarization power. Okay, so I hope we are clear with all of these factors, the three factors that we discussed over here. Obviously the first one was the size of cation and anion. Okay, the next one was charge. As the charge increases, the covalent character increases. So you can just write down over here quickly before we wind up for this session. Okay, I'll just try to write down. So for covalent character, what I would say, for covalent character, I would say that charges, as the charges increases, the covalent character increases. Okay, because obviously the polarization and polarizability increases. Again, let me repeat, for anions I'm just focusing on magnitude and not the size. Okay, next. Okay, so if I talk about the size, for size we have already written down over here. Size of anion is directly proportional to the covalent character, and size of cation is inversely proportional to the covalent character. And last one is the pseudo noble gas configuration. Pseudo noble gas configuration is NS2, NP6, ND10 cations. Remember, this is only for cations, not for anions. Okay, and let's take an example of copper. So CuCl and CuCl2. CuCl will have more covalent character because of why? Because it is having a noble gas configuration or a pseudo noble gas configuration, whereas CuCl2 will have a less covalent character because he is having a normal configuration, or I would say he is not having a pseudo noble gas configuration. Okay, then similarly we also discussed about that which are the anions that could give you pseudo noble gas configuration. Then let me just cancel Cu2 plus over here. Okay, we'll just write down the anions which has pseudo noble gas configuration. So those are Cu+1, Ag+1, Au+1, or Zn+2, Cd+2, and Hg+2. All of these 6 ions have pseudo noble gas configuration, so they have the capability of showing you the maximum covalent character. Okay, so I hope this thing is clear up till now. In the next session we will be discussing about few questions based on Fajans rule. Till then, thank you, students.